is definitely the near field. But they don't call it the capacitive coupling test. They call it the radiated electric field test, which is crazy, right? If you are, think about what that means. If you're looking for, I can't remember, I can't do the math up in front of you, but whatever the wavelength is at 150 kilohertz, it's whatever, 100 kilometers, right? You will spend the rest of your career looking for a piece of cable that's close to 100 kilometers on a real product. It's not necessary to cause a radiated electric field test failure because we're in so close, the measurement antenna is so close to the source that little tiny objects can cause trouble, right? So the ideas that you use for troubleshooting many commercial radiated emissions tests will be quite different than the antenna concepts that you wouldn't use for troubleshooting an automotive or aerospace emissions test. There are different levels for the different standards. For trying to protect a GPS system on board an automobile, we need a tiny little level because we want noise to be very low on the vehicle because we're listening for a tiny little signal from space, right? If we're in the far field, it doesn't really matter what our antenna looks like. As long as it's calibrated, we'll get the right corrected measurement of the field. But if we're in the near field, then if we think about capacitive coupling for a second, that means the size and shape of our antenna might matter, right? So we might find out that if we put our antenna a 2,000th of a wavelength, if we bring it so close to the source that it looks like we have capacitive coupling, that the size and shape of the antenna would matter. And we might not be able to correlate one person's radiated electric field test to somebody else's unless we had the same make and model antenna. So if you've been in the EMC world for a little while, you know that we do some kind of crazy things when we're measuring when we're doing some radiated emissions tests. Most of them have some significant flaws to them. Okay? Any questions? Very quiet. Okay. There's no noise. Okay, excellent. All right, so what's the consequence of being in the far field or not being in the far field? If you're in the far field, the antenna factor, the calibration information from the vendor of the antenna is good enough to get to be able to tell me what my corrected final value of electric field is right here at the measurement system. And we can neglect the size and shape of the measurement antenna. Just give me a calibrated antenna. If they look different, I ought to be able to get essentially the same measurement from one test lab to another lab. Okay? In the far field, we can linearly extrapolate the test limits. In other words, if one person uses a 3-meter test distance and we show with math that they are measuring in the far field, and then another person measures the same product at 10 meters away, and we can mathematically show that that was done in the far field, then we ought to just be able to take we ought to be able to just change the test limit or extrapolate the field that we believe we will measure by taking 20 log of the ratio of the two different distances, right? But that depends on believing that when we move the antenna from 3 meters to 10 meters, that the field strength falls off at 1 over R. The field changes as 1 over R. That means we are in the far field. You can't start in the near field and then go to the far field and use 20 log 1 over R, the ratio of the two distances. That doesn't work. Okay? So if we are in the far field, we can extrapolate the test limits from one distance to another. In the far field, we can ignore inductive and capacitive coupling to the measurement antenna. We only care about the 1 over R fields. Okay? In the far field, small electrical objects, so long as they're not all clumping together to make something big, small electrical objects can be ignored. So I don't worry about my little audio transformer causing a radiated field 10 meters away at audio frequencies. I don't worry about the little audio coupling capacitors, the 10 microfarad capacitor, which is allowing 1 kilohertz to go in and out of my audio amplifier okay. I don't worry about that capacitor forming an effective antenna, right? I ignore that. But if I'm working way in the near field, then that transformer could be the source of capacitive coupling to the measurement antenna. The little display, the vacuum fluorescent display with voltages on little tiny electrodes, that could actually be the metal coupling to the receiving antenna. I've worked on those sorts of problems, right? So in the far field, small electrical objects can be ignored. So we just focus on the big long wires or the large sections of circuit board or the large portions of our enclosure. It makes troubleshooting easier. Okay? So that's what's all true in the far field. But in the near field, let's just replace can with cannot. You can't, the antenna factor isn't good enough if you're trying to use a far field antenna factor with the measurement antenna in the near field. You can't linearly extrapolate test limits when you change distance. You can't use a 1/r rule. If you're in the near field, you can't ignore inductive and capacitive coupling. That's precisely what we mean by near field coupling. And in the far field, you can't ignore electrically small objects. Oh my gosh, not everything in the system, but lots of things in the system could cause me to fail the stupid aerospace or automotive radiated electric field test at frequencies below a megahertz, at frequencies below, well, let's see, at 30 megahertz at 1 meter, we're a tenth of a wavelength away, right? That's pretty close. That's a near field to anybody. But then we make those measurements at much lower frequency, much longer wavelengths, okay? So that's kind of repeating myself. Okay, so that's about radiated fields. We just talked about radiative coupling. Any questions about what of course, there's no questions. No? Yes? The question was, what's the difference between electric field probes and magnetic field probes, and how to use those to detect noise? Yeah, so the near field probes, we talked about that a little bit earlier, but we could use, so the probes that many people use for troubleshooting noise, many people use a loop that has an almost complete metal wrapper around it to stop electric field, but allow a magnetic flux to pass through the loop without generating an equal and opposite magnetic flux. That's what would happen if they completely covered it up. So they use a loop with a little hole or cut in the shield, and that helps us find time-changing currents. So we could use that to find antenna current, the current flowing on an antenna that's causing a radiated electric field, radiated electromagnetic field. And then we can use electric field probes, which will generally look like a very small, if you imagine a coaxial cable, something with a very small piece of metal extending out of the coaxial cable to provide electric field coupling from that surface to another surface. Our bodies, you're a walking capacitor, right? We have an absolute, if you were in outer space, you would have an absolute capacitance of 50, 60 picofarads. If you're in the room, you're next to all sorts of metal. You're or on the order of 100 picofarads. So if you use an electric field probe, your body kind of gets involved, and so do metal objects nearby. So using an electric field probe can be a little more challenging, but people use both. So when to use an amplifier with a near field probe? Only when you have to is the right answer. So you're asking a couple of questions at once. I'll talk to you about one right after I'm done talking. As far as the amplifier question goes, if you choose or build if you properly select, you properly choose or you build a magnetic field probe that's appropriate for the frequency, if you're working on a regulatory noise problem, except for it depends, but except for maybe GPS and wireless radio interference, if you're just working on a regulatory noise problem, usually you don't need a preamplifier if you've picked the right probe and you have a good test receiver or spectrum analyzer, which will often have a built-in preamplifier. Usually the radiated limits are big enough that the source current you're trying to measure is pretty big. So normally amplification isn't necessary. There are plenty of special cases. Okay, the other one. Okay. Yes? Sure, if you were, yeah, I mean, I guess I would argue, so if you're using an oscilloscope and you're trying to look at signals that are very small, the scope is often going to not have the sensitivity that a purely, RF domain instrument. There are a lot of depends in that. But I would generally agree that if I want to see, if I'm measuring a small noise signal, I can easily display it on a test receiver or spectrum analyzer in the frequency domain. It might not be nearly so easy on a scope. That's kind of where I would put it. How I would put that. Anybody else? Yes. Is it possible to build a far field model from a near field model? I am not an expert in that area. I would say that if you know the antenna structure very well, if you know exactly what is the structure of the antenna that's going to produce the far field, then I do believe there are techniques for looking at the near field and then estimating the far field from that, so long as you know what the antenna structure really is. In many cases, in radiated EMI troubleshooting, we don't have such a model. If you're building a mobile phone or a GPS system, you know exactly what the antenna is going to look like, and you can model the near fields as well as the far fields quite well. I think that would be that might be a good question for Dr. Hubing in the back of the room when he comes up. Save that question for him. Okay. Anybody else? Okay. Next, we're going to talk about antennas for radiated emissions, antennas that cause radiated emissions. So my favorite friend is a dipole antenna, and children, no matter what part of the world they grow up in, they learn how to count first in their language. So they say, 1, 2, uno, dos, ein, tres. They count to 2. If you can count to 2, you can find the antenna in most radiated emissions problems. Not all of them, but in a large majority of radiated emissions problems, you just need to find 2 pieces of metal that are not well connected together, which is why I like to teach electromagnetic compatibility to mechanical engineers, because I want them to count the pieces of metal in system enclosures that they build. And as soon as they count 2 distinct pieces of metal that are not well connected, I say there is the possibility for an antenna. We have to talk about the size of the metal next to say if that size, those 2 pieces of metal will be efficient antennas or not, whether they're big enough or not, but that's where we start, counting 2 pieces of metal. So the dipole that you might have learned about in school, it's a quick refresher. You know that the right length for it to work perfectly is a half wavelength tip to tip, right? So if we talked about a 100 megahertz an FM radio signal, we would say lambda is equal to the speed of light divided by frequency. So we'd come up with 100 megahertz, we'd come up with 3 meters. So that means for an FM radio antenna, it would be 1.5 meters tip to tip, or it would be 75 centimeters on either side. So if I had a demonstration here in front of you, I would point to a cable, say a DC power cable attached to my demonstration that had significant physical length. We would find that that was the cable carrying a conduction current at 100 megahertz. That was the cable that was causing a radiated emission at a distance. That cable would be one half of the antenna. The other half of the antenna I'll talk about in a second. So generally speaking, a dipole antenna, two pieces of metal, and good antennas must have 2 pieces that are greater than at least greater than let's say 1/10 of a wavelength. There's no perfect answer there, but greater than some very small piece. Okay. Now in EMI talk we have some funny ways of talking about things. If you are an antenna engineer and you talk about what makes a good antenna, you will say, well, the antenna must have exactly this shape, this exact geometry, the pieces of metal must be this long, they must be this wide, and if you're just building a dipole antenna, you would say each half must be a quarter wavelength, maybe a very small adjustment to get the reactive part of the input impedance to be 0, but you would point to a quarter wavelength on each side. You'd say that's what makes a good antenna. So in EMI talk, we talk about each piece being greater than some trivial size, but if the cable is, if your antenna structure, let's say a wire leaving a circuit board, together with the size of the circuit board being the right length, we say that will make an excellent antenna, and you will fail the radiated EMI test, or you will fail the radiated immunity test. But then what customers always ask us is, say, well, Lee, what if the cable isn't the right length? What if I pick a 20-meter Ethernet cable instead of the 10-meter Ethernet cable? Will that stop my higher frequency noise problems? And my general answer is no, it won't, because we EMI people, we have a funny idea. We say if the antenna, it's not going to be too long. We're going to say it's good enough. Once we have a sufficient size piece of metal for the two different pieces of our dipole antenna, we're going to say that can still cause a noise problem. You'll still fail the EMI test. You might not fail it by quite as much or as easily, but we do not ignore pieces of metal that are larger than a quarter wavelength. And if you're an antenna engineer, that will make you crazy. You'll say, I could never design an antenna if it was the wrong length. But in reality, if we're worried about radiated emissions, lots of times from digital systems that are producing many harmonics, right? We have excitation across a very wide frequency range, right? At a few of those frequencies, our attached cables, the metal structure surrounding the circuit board will be resonant, will be a nice length, and we'll have a very bad emissions problem or a very bad immunity problem. At all the other frequencies, those antennas are not the right length. There is not some really mean person hiding behind your product, adjusting the cables to be the right length at every frequency that's coming out of the product. At many frequencies, those cables are the wrong length. But many of the radiated emissions tests are looking for very tiny signals, right? So it doesn't take a perfectly tuned antenna to cause trouble. Many of the military and automotive immunity tests are generating a very strong field surrounding your product, immersing your product in a very strong field. And it doesn't take a resonant antenna to couple enough power into your product to cause an immunity failure. So we talk about antennas that are too short, they don't work very well. If they're the right length, of course, we'll have an emissions or an immunity problem. And if they're too long, we say, oh, you could still have trouble. Yet switching to a longer cable does not hide a radiated immunity or a radiated emissions problem. Changing to a very short cable, however, could hide a low frequency radiated emissions or radiated immunity problem. Okay? Those are some basic concepts that you can take and use when you're working on a real product. Any questions? Okay. So dipoles. Here are some easy to see dipole antennas. I just showed you one of them. In the old days, in the last century, you would go to the university and you would find students in their university dormitories, in their residence housing, and you would find pieces of wire up on the wall so they could listen to FM radio stations. And those pieces of wire were about 1.5 meters tip to tip. They were listening to FM radio stations, right? In automobiles, there are things called, that are often called mast antennas. That means the piece of metal sticking up out of the car, right? And still some automobiles today still have these mast antennas where there's metal sticking up out of the car. If you are to look at the radio and follow the cable from the radio to the antenna, the cable is probably coaxial, so it has two conductors, right? The center conductor is connected to the mast, the piece of metal sticking out, and the second conductor of the radio cable is connected to the car body. The car chassis is made out of metal. So those are the two pieces of metal. If the mast breaks off, and you look at your car and say, oh, the antenna's broken, you know that your radio will not work well. If somebody walks up to your car when you are not around, somebody goes to your car and they say, wow, that is a beautiful car. They have the terrible radio from the factory. They did not buy the super expensive radio, but nice car. They steal your car, but they leave the mast and the radio behind. The radio still does not work because they took away the second piece of metal, the car body, right? If you are in a boat that does not have metal the hull, the outside skin of the boat is not made of metal. There usually is another piece of metal somewhere to make the second half. Radio people, they make up all sorts of crazy names for that second piece of metal. They call it the ground plane, the radials, the counterpoise. They have all these extra words made up, but really all it means is the second piece of metal. If the antenna is symmetrical, they say, oh, well, that's two halves of a dipole. As soon as the antenna is not symmetrical, they create all sorts of unnecessary names for the second piece of metal. I'll just point that out, okay? Now, what if you are a true noise geek and you want to ruin the performance of somebody's FM radio in their car, but you know that if you break off the mast, they will notice right away. That would not be any fun, okay? So what do? You walk up to the car. Please don't do this, okay? But you walk up to the person's car, and when no one is looking, you take away some of the paint right where the mast is leaving the car body, is exiting the car body. You take away a little bit of paint, and then you take a very small wire, a very, 0.5 millimeter wire, and you connect the mast to the car body. Their FM radio doesn't work anymore, right? If you're Mr. Thevenin, as we say back home, you've shorted out the antenna, right? You've made two pieces of metal into one. Right? If you like Mr. Norton, you have diverted the noise current back to where it came from, which is essentially the outside world where the radio wave originally caused it, right? So doesn't that sound familiar? Doesn't that sound familiar if we build a system with a conductive enclosure and a circuit board inside, and we have a single wire leaving that box? It doesn't matter what that wire is called. It could be called ground. It could be called earth ground. It could be called +5. It could have any name that you want, but if it could be a pipe, a piece of metal. If you have that wire exiting the box, lots of times people try very hard. They put things between the... What component do they like to put between the wire and the box? Have you seen this on a circuit schematic? People like to put a capacitor between the wire and the box, right? All current flows in a loop. All current wants to return to its source. So for an emissions problem, we're sending the current that started on the inside. We want that current to return back to where it came from, to the inside. For radiated immunity problems, I know this is a radiated emissions talk, but it's really the same thing, isn't it? It's just the direction of the noise current. If we have a radiated immunity field causing a current to enter the product, that capacitor is trying to return it back to the outside, back to where it came from, right? We would like to directly connect every single wire to that conductive enclosure. We're not allowed to, right? You're not allowed to connect the AC mains to the enclosure directly. That would be bad, right? You're not allowed to connect the 12 volts battery in the car directly to the car body. That would not be smart, right? Where we are allowed to, we would. If that was a 0 volt wire and there were no other concerns, no other system concerns, if I had a DC return or an AC signal return wire, and I was allowed to, I would like to connect that directly to the box, as well as every other wire, but I can't. So we think about those capacitors as connecting the wires to the box or this conductive enclosure at what we might call high frequencies and not connecting it at low frequency. So what we're really trying to do on the frequency axis, what we're trying to do is we're trying to build some sort of filter that will not bother the signals, but will do something bad to the noise. So we need something, a capacitor, something that has a low impedance at noise frequencies to short out the noise, but will let my signal go through. And for DC and AC power supplies, for low frequency AC communications, we can use that capacitor. There may be reasons why we cannot use that capacitor in, say, in a medical product, but where we could, shorting out the two pieces of metal, that's basically what we're doing to control radiated emissions. That's what we're doing to control conducted emissions, right? There are capacitors inside of our DC and AC line filters. If the noise current reaches the detection network, the artificial mains network, or the line impedance stabilization network, we're going to fail the conducted EMI test. If we can redirect that noise current back to the product and not send it to the artificial network, then we'll pass the conducted emissions test. Okay, it's about time for a break. Any other questions before we go take a break? What time is the end of break, Art? 20 minutes. So we're back here at 10:20, please. Thank you.
With part of the rated, and he will start with the conducted emissions part. So welcome again.